So this is a standalone topic on circular motion. It doesn't really relate all that closely to the other things, but the concept's the same. It is vectors. The chances are this is one dot point. It's actually half a dot point on the syllabus. It's the half a dot point with projectile motion, but the difference is there's not much of this in the PSMT. You might get a question on this in the exam, so know the stuff. You might get a question in the external exam, but you probably wouldn't get more than one question in each. So you need to know it for that one question though. So has anybody ever seen somebody, this was popular when I was a kid and I'd go camping, and somebody tie a billy. Do you know what a billy is? No, so a billy's like just a can that you boil water over an open fire with. It's got a handle. Somebody tie that to a piece of string, fill it up with water, and start with it down here, and just spin it around like this, and the water wouldn't come out, even though at one point it was upside down. And you probably know from a physics context why that is, because the motion is driving an acceleration outwards from the circle, and that holds the water in because that acceleration is overpowering the gravity acceleration, so the water stays in the can. That's pretty much what circular motion is, doing this, spinning around. So another example is like a Ferris wheel is in circular motion, for example. We're going to talk about the rules and how circular motion works in vector form. But as long as you know that it's really closely linked to periodic functions, and some of you are doing that work at the moment where you convert a vector form into Cartesian form, and you're going from periodic functions into a circle equation, and this is part of that as well. So it's the context of that. So if you have an object that's swinging around a circle, there are a few things that we can define. First, we have a position vector. That will be xy, which we can write as xi plus yi, as we've done, and it will often look like this: r cos I plus r sin I. You can swap the cos and the sine around. Chris just had a question earlier that had sec and tan. That could potentially work as well. And it's a circle, so r will be the same. As some of you have experienced, if r is not the same in your Cartesian form, you get an ellipse. Now, all the contexts we deal with will be circular, but obviously, like planetary motion around the sun, that's elliptical, it's not circular. So there are some things that you could model that have got the circular motion context, but they're elliptical and they're a little bit different. The magnitude of this circle, of this motion, is that. And when you simplify that, it's r, which makes sense because the magnitude of this point going around a circle is always just the radius. That's the definition of a circle. So that point will always be r away from the centre because it's on a circle. And so when we calculate the magnitude, we should get r, which we do. So it's set up, it makes sense. And then we also have theta, which is measured from the positive horizontal axes, as are almost every angle, except in the case of bearings. So positive horizontal axis, theta is measured from there. And it's a measure of angular change, and it's going to be quite important. So first of all, we have angular velocity. And angular velocity is omega. And I'm going to just be honest with you right now. I could call it either omega or omega. Because I got in a situation where I went to a little country school. My teacher called it omega, which has then ingrained itself in my head. And so I'll try and call it omega, but I may call it omega, and I'm sorry in advance for any pain. I've caused people pain in the past. They've told me it's been really painful, and I apologise. So omega is the angular velocity, which means that it's the change in the angle and it's the rate of change of theta. So in actual fact, that's why we can say that omega is not working. That one's working, there we go. Is this thing here. That's delta theta over delta t, which is our average rate of change of theta over time. But actually, circular motion will move at a constant speed, not a constant velocity. The velocity is changing because the direction is changing, but at a constant speed around the circle, unless there's some other force being applied to it. And so this average change in theta over the average change in t will actually be the instantaneous rate of change, because it will be moving at the same speed around the circle. So we have, because of that, because the average is the same as the instantaneous, we can say that omega equals theta over t. which means that we can say that theta is equal to the angular velocity multiplied by the time, which makes sense. So if it's moving at 60 degrees per minute and it moves for 4 minutes, it's going to move up 240 degrees. Yeah? So that's our first formula, and I'll summarise these formulas in a minute. Technically, omega is the theta to t, which is the IROC, which I've written there. But as I've said, circular motion, the velocity is changing because the direction's changing, but the speed is staying the same. So it'll move at a consistent speed. So if you imagine a Ferris wheel, you go around a Ferris wheel at a consistent speed, but your direction does change. So they're kind of the same thing, and we can treat them the same, which is where this comes from. Additionally, we know this. We're going back to the periodic function component here. We know that the period is equal to t, and the period is the time taken for each revolution, which is where the context works really nicely. A revolution on a Ferris wheel is a pretty obvious measure and an important measure in a lot of cases. But t is also the theta, which is our angle, and in this case, a full revolution is 2 pi. So you see that link with the b and the t as well. Omega is the angular velocity, so it's theta per second, whereas the period is just theta. And so we get this as well. We get that t is equal to 2 pi over the angular velocity. That'll be our period, or the angular velocity is equal to 2 pi over t. And hopefully you recognise here that means there's a fairly direct connection between the angular velocity and, if you cast your minds back to term 2 math methods, the b value in a periodic function. And when I say fairly direct, I mean exactly direct. They're the same thing in this context. Like b, and so we have, instead of saying r cos theta, we say that the position vector is equal to r cos angular velocity times time, because that gives us a value for our angle that we travel, plus r sine angular velocity times time. You still have to be careful here with your initial positions though. Your position might not initially be at, because we're talking about theta, at theta equals 0. And that will be the positive horizontal axis over here. Often, with a lot of context, like a Ferris wheel, your initial position will be down here. And theta will be negative 90 or 270, whatever you're dealing with. So just be careful that you're careful with that. So we can work out our velocity from that. So our velocity function is equal to r, oh, that's not an r, that out, r omega cos omega t I plus, and that's not cos, and that's a negative, sine, there we go, that's better. This always happens when I'm filming it. Let's pretend that's true. So there's my derivative, so that's my velocity function. Everybody happy with that? And in some contexts, although it's rare, you might find it useful to recognize that this is similar to the position, but not quite, by taking out that common factor of omega, and you can take out the common factor of r as well, but it does look a little bit like that. Plus so there is that element to it, but the velocity doesn't relate nicely to displacement or acceleration. Acceleration and displacement relate really nicely to each other though, and I'll show you that in a minute, because sine and cosine, when you derive them, they oscillate. So they go, cos goes from cos to sine back to cos, so you actually get this nice relationship at the second derivative level. Chris? This is just me showing you that it might be useful to recognise that W is equal to something that could be a position vector. That is another version of this. So I haven't taken out R because we didn't take out R as a position vector. You could take out R. So that's up to you. I would actually say that you're probably going to use that one. You're probably not going to use that second one I've written down. That reason. Now, we know the speed. The speed of this thing is equal to the magnitude of Vt, which is equal to the square root of negative r omega cos, and by cos I mean sine, That squared plus r omega cos that squared, that's equal to the square root of r squared omega squared sine squared that plus this. Now, I've given myself just one more line, so we'll say that you could take out sine squared, cos squared as a common factor. We take out r squared omega squared as a common factor. You're left with sine squared plus cos squared, which is 1, and the square root of r squared omega squared is just r omega. So you can simplify that, and you get the speed is equal to the radius times the angular velocity. And that kind of makes sense as well, because that is a measure of the sector, the arc length. So this is, if you go back to your work in year 10 measurement, you'll know the arc length is equal to the radius times by the angle that's measured around a circle. Usually that angle is measured as a proportion, but the whole concept of radians is that we don't have to measure a proportion, because a radian represents the distance around the circle for a radius of 1. So there we go, speed is equal to r omega. And the acceleration is equal to the derivative of velocity, which is equal to, there's my velocity. I've got negative r omega sine omega t I becomes negative, stays negative, r omega squared cos omega t I. So I've derived the first term. And then the second one becomes negative because cos goes to negative sine, r omega squared sine omega t. I don't know why I put that first bucket there. Let me just swap that out. J. Whoop. So there's my derivative. If I take out, and this will be important if you're wondering, if I take out the negative omega squared, I end up with, and you'll notice here that I'm not taking out the r cos omega t I plus r sine omega t j, and that was just our displacement model. So we get, I've got lots of weirdly placed equal signs here, let me just get rid of that. That equals negative omega squared. So the acceleration is equal to negative the angular velocity squared times by x, which is your displacement. Okay, now if we go and have a look at a diagram, that gives us a really interesting result. So here's a diagram with position, velocity, and acceleration. We have a look at this diagram here. The position is the green one. The position is just from the center, because the position is measured from the origin, around here, wherever it is. The velocity is always going this way. So if I'm spinning that billy can, or your Ferris wheel is moving, it's always moving, so it's perpendicular. It's basically a tangent to the circle. Moving around there, it's a tangent to the circle. The velocity is changing direction, but the magnitude of velocity stays the same, because that's our angular velocity. And then the acceleration is drawing us back in, which is why our object doesn't fly out. In terms of the billy can, that acceleration is actually the tension in the string that I've got. We talked about tension last year. It's drawing it back in. And you'll notice here, and this happens a lot with vectors and complex numbers, that displacement is in that direction, and then velocity is in this direction, a 90 degrees rotation, and then acceleration is back in at a 90 degree rotation. Now, I've sort of represented acceleration as being shorter than position, which is not strictly true, because remember, acceleration is the negative of displacement. That's why it's in the opposite direction. Omega squared is the factor here, and omega squared, if omega is 0.8, then that's going to be less than 1, which means acceleration will be shorter. But if omega is 2, the acceleration will be larger. So it depends on what your angular velocity is. So there's that understanding, and these are the things that you need to know. And then I have, oh yeah, there's stuff to know. What's the good stuff? I think that actually might all be there. This might be a better summary. I think I rewrote the summary and didn't write about the old one. So there's the stuff you need to know. This is the extra notation. It's the notation, I've said this a couple of times, the dot notation has come through our studies in physics. So you're more likely to see that in a physics context. It won't come up I won't use that in your exams. It might come up in the external exam. It might come up in a resource you're looking at. So I want you to see the dot notation. X dot just means velocity. It means dash. It's the same as X dash, same as dx dt, whatever. So there's what we've just done. Summary, speed, the relationships here. To start with these questions, the best thing is to have this summary next to you and just revert back to the particular questions you need and the formulas you need. But you also need to be able to develop these formulas. To understand the basis of them and be able to develop them. To do that, you need to know what the position vector looks like, and you need to understand what speed is and what angular speed is, omega initially, as the rate of change of theta over time, and you can build everything else from that. Yeah.
In a test, we need to derive the acceleration.
There might be a simple familiar question or two where you can just use that, basically. There's nothing nice in the projectile motion stuff. You probably have to do all those. But again, you might, like if it was something like I drop a ball and you just knew enough about acceleration, it was a simple familiar, you could probably do that. But in this case, if it was a 2-mark simple familiar question that said, gave you some information about the rate of the angular velocity and your position, and you had to find the acceleration, then that would be fine. Yeah. So just got to watch the question. I think the textbook does a pretty good job at staggering them out, although it does gear more towards the 4 or 5 part build and answer type question. I have a couple of examples, but what I'm going to do is I'm just going to leave that there and let you make a summary and maybe do a couple of textbook questions. It's 10:14, so we've only got 10 minutes left.